Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would like to wrap up my story about graph polynomials by just summarizing what at least I know the Tutte polynomial is counting. I will recall what we actually already have seen, but if the point is, then kind of the whole point I wanted to make about graph polynomials, that they are counting a lot. And as soon as you kind of have discovered the first graph polynomial, then they are just a zillion generalizations. So I'm just stopping here with the Tutte polynomial because it's still fairly easy and very powerful, but there are many, many versions which count quite a lot of things. And remember that counting is usually a bit difficult. And the point here is that one thing, one polynomial, counts like zillions of things. And we will see at least the list, kind of the incomplete list, obviously, that I have here today of what I know the Tutte polynomial is counting. There are probably way more things. Okay, so the starting point in our whole discussion was counting colorings. And there was this chromatic polynomial, and it was really beautiful. So p at k, so there's one variable polynomial, chromatic polynomial. And if you specialize x to a number k, then you count the number of colorings. So in other words, if you think of here my little picture here, if you have a fixed graph G and you list the number of colorings somewhere, that's a really bad picture, but anyway, then there's a unique polynomial that goes through all those points, and that's my little polynomial pg of x. This is a really ugly G, so let me get rid of the G here, and let me just try again. So that's a much better G. Anyway, so this polynomial counts obviously something very important, the number of colorings. So, well, whether that's very important, anyway, it counts something very important, the number of colorings. And since that polynomial specializes to the chromatic polynomial essentially by setting y to 0, there was some normalization issue, but essentially setting y to 0 specializes the polynomial. Clearly, then, the Tutte polynomial already counts colorings as well, which is quite impressive already. But you might argue, okay, the other polynomial already counts this, so why do I need an extra variable? Well, and now we really want to use the extra variable, right? So here y is 0, and whenever y is not 0, something different is counting, which is kind of very, very, very great, right? You're counting colorings for one specialization, you're counting something completely different for another specialization. So here, completely different things you can count. Note that this one here is actually equal to the number of colorings up to some scaling. So this is the only one that has y equals 0. So here are my specializations. So you count forests, you count spanning forests, you spanning subgraphs, acyclic orientations, strongly connected orientations, number of edges, a lot of things. You just specialize at very small points here. So x equals 2 and y equals y, for example. And you count several kind of statistics associated to your graph, which are not completely trivial to count if you think about it, just trying to do it brute force. So for example, we have this counting of forests and trees, counting of subgraphs, counting of orientations, and all of that roughly happens around those little values here, which is kind of really good. So here we had y equals 0, but k gets arbitrarily large, so k goes to infinity here if you want. And here we're kind of using y, but we are keeping, we are kind of staying in this area of not too large numbers. Yeah, it's really, really impressive. So one polynomial counts very different things: colorings, forests, subgraphs, orientations, blah, a lot of things. And this is just a very incomplete list. And there's way more known. So this one is pretty cool. So the one where y equals x is another specialization you could look at. So if you think of this graph here, y equals x is kind of this line, y equals x. And for all of these, for all integer points, this actually counts something. So it always counts something. It's a bit difficult to say what it counts, but let me try at least. So for any planar graph, you have, or I should say, plane graph embedded in the plane. So planar plus embedding, like this one here, plus embedding, like this one here, you could form what is called the medial graph. Essentially, well, this one is a good picture, by just putting a vertex on every edge and then kind of connect along consecutive faces, and you get another graph associated to the embedding of your graph. So here and here, right, you put a vertex here at every edge, and then you just connect around the faces, and you do that in the middle as well, and you get the graph on the right. So this is the medial graph, and it's absolutely not clear why the Tutte polynomial should know anything about that graph. Note in particular that this graph, or you can't note that, let me just say, in particular, this graph depends on the embedding. So if you choose a different embedding, then the graph might be different, okay? And the Tutte polynomial does not detect any embeddings. So what should be the relationship here? And it turns out that there's a really good relationship. So for along this half, so this is my a bigger than 0, it counts edge colorings related to that graph. So some coloring, but for a very different graph. And along here, which is my a smaller than 1, so the point 1 is somewhere here. Anyway, it counts connected components, again, of the medial graph, which is very surprising because the Tutte polynomial is independent of the embedding, and the medial graph is not. And this would be a way how to prove that these number of colorings and connected components are independent of the embedding of the graph, which is not quite clear, which is really not clear at all. I think this is a pretty cool counting. It's a bit difficult to state, but kind of the x-axis, so along this green line, everything counts something, and it's related to a very different graph, which is kind of very fun. And you can prove things about that graph using the kind of the Tutte polynomial itself, which is pretty cool. So this is very different. And again, of course, and now you have 1, 1 here. So 1, 1 is exactly the point that I took out here, as you can see. But 2, 2, for example, 2, 2 would count something edge colorings on this graph, a certain type of coloring. And by Tutte counting, this would be the same as the number of this number here, 2 to the number of edges, which is, again, not clear at all. So it's kind of pretty cool, actually. Okay, so counting can be really hard. So 1, 2, 3, 5, start again. So I'm very impressed that the beans here can already count up to whatever, 3. I can't count up to 3. So counting can be very hard. And the Tutte polynomial somehow is one closed formula, if you want, that counts many different things associated to the graph. So one polynomial to count them all. And it's really impressive. So sometimes, so for example, T33 counts 2 different things, and they're then the same. So here, anti-circuits and edge colorings, very different kind of. Still, it's counted by the Tutte polynomial. But it gets even better. It gets even better. So you might wonder, okay, all of these are kind of integer points. So here, integer points along this line, all integer points, here, integer points. So what about non-integer points? And it still counts something for non-integer point, which is really exciting. Essentially, this is related to random graphs, the next topic I'm going to cover in this series. So essentially, for today, just the GP be the graph obtained from another graph by keeping edges with a certain probability. So essentially, you have a fixed graph, you flip a coin, potentially a biased coin, and whatever your coin says, you either keep the graph or you drop it. And then you can look at the Tutte polynomial at this value here, which is clearly not an integer value because you have 1 plus 1 over p, and that's p is 1. But let's say p is something like a half, and this would be the expectation value of the number of forests in the graph, which is kind of cool. So, so non-integer points often count something related like expectation values of random graphs, and that's kind of very great. I mean, not just the integer points count something interesting, also the non-integer points count something interesting. Anyway, kind of this was just my wrap up of the story of graph polynomials. As I said, there are way more graph polynomials than I was able to cover, but the Tutte polynomial is already so impressive. At integer points, it counts very different things: forests, colorings, colorings associated to different graphs, and it's quite a lot. Not quite a mess, but it's quite a lot. And at non-integer points, it tends to count kind of things for random graphs, so expectation values for something. So as we have seen here, so for p equals 1, this would be 2, 1. And if you remember, or probably you don't, but anyway, the 2, 1 would be the number of forests anyway. And that's probability 1. So you keep an edge with probability 1. So you count the number of forests. And if you vary that by throwing in a smaller probability, then you can count off the expectation value of that graph. And I think I personally like that a lot. I hope you like it as well. Anyway, I hope you enjoyed this video, and I also hope to see you next time.